So today I'll start with the diffusion flames, non-premix flames. And then another one is, emissions. So emissions probably will take, 2 sessions, not more than 2. Okay. And then Professor Kushari, he's going to cover, droplet combustion, droplet evaporation and combustion. And then Professor Shogde, he'll do some, problems, examples in the class. Okay. Okay, so I'll start with the diffusion flames. Okay, for analysis and for research, okay, diffusion flames, have been studied in several configurations. So 3 main, are the jet flame. That's probably the more common configuration to study jet flames. And then counterflow. Okay, so I'll show some images of counterflow. I think we have seen some already. And then for droplet, okay, those are spherical flames. Okay. And of course, real flames, are not like 1-dimensional or 2-dimensional. They may be 3-dimensional. And the geometry can be a combination of, all other simple geometry. So we are going to discuss mainly the jet flame, and I'll show some results for spherical. Then for droplet flames, which are the counterflow, I'll show some results. And then spherical flames, Professor Kushari will deal with that aspect. So here are some images of jet flame, and you have seen this before. So a fuel jet coming out from a tube, air is outside, and then you get the flame. Again, emphasizing. So here, this is, you can call the flame, and at the tip you have the soot, being formed. So again, the structure is that the flame is here, and then you have the fuel inside, which is being transported or diffusing, okay, to the flame surface, and oxygen is coming from the other side. Okay, these are some images of the same flame computed in now in 0 gravity. So this also you have seen the droplet flame. So this is the droplet, okay, and then it's ignited somewhere. Okay, there you can see how it is ignited, and then after ignition, the flame is established. Under microgravity condition, it will be spherical. So if it is not microgravity, there is a effect of gravity. Then you can imagine how the flame shape will change. So first under 0 gravity, you have the droplet. Okay. So when you ignite it initially, so there are 2 ways. You can have this droplet, okay, injected into a hot environment. Okay. So then it's like auto ignition. So the temperature of the ambient temperature of the environment is high enough. Okay. So the vaporization will start. Okay. So fuel vapor will react with that air, and initially the ignition will occur in a premix condition. The fuel vapor and air have to mix. Okay. So there will be some premixed condition where the ignition will occur. But then the premixed flame will extinguish, or the premixed combustion will diminish, and then eventually you'll have a diffusion flame outside. So now the fuel vapor is coming, okay, from the droplet. So if you look at the mass fraction distribution versus the radial direction, so YF value is the highest at the droplet. Okay. It may be close to 1. Okay. And then this is the flame. So then it decreases, okay, as you go toward the flame. Oxidizer, on the other hand, is highest in the ambient, so YO2. Okay. So this is the typical behavior. Then the fuel and oxygen mass fraction, they go to almost 0, okay, near at the flame surface. Okay. And of course, the product, first of all, the temperature, the droplet temperature is relatively low, but it's higher than the ambient. Okay. And then the temperature, if you plot, we have the peak value at the flame, and then it will drop. This is the variation of the temperature. Okay. And you can imagine that this temperature will be close to the adiabatic flame temperature. Okay. And similarly, you can plot other species like the CO2, H2O. They will have their peak value at the flame, and then will drop off on both sides. Okay. Now, this structure is similar whether you have a jet flame or counterflow flames. Okay. So, the basic structure is similar, that at the flame surface you are transporting fuel from one side and oxygen from the other side. Okay. And combustion is occurring at near the flame surface. Okay. Now, I was saying, the flame is spherical under microgravity condition. Now, if you have gravity effect on this droplet, so this flame will have this shape because the buoyancy. Okay. So, the light gases, the product species, there is a buoyancy effect. So, there is a buoyant convection, so that will make the flame this, this shape. So, 2-dimensional or 3-dimensional. Okay. So, then the analysis also becomes more complicated. So, for jet flames, these two configurations have been commonly used. This is the more common one, the two co-flowing jets, the fuel jet and then the air jet from outside. And then you can control the velocities of the fuel jet and the air jet to control the different flame properties. Okay. For partially premixed flames, you also add some air to the fuel jet, and other possibility, you have some air to the fuel jet, so you have a fuel-rich mixture in the fuel jet, and then you can also add some fuel. Okay, you can add some fuel in the air jet, so then you can get triple flame. So for standard, for diffusion flames, you have fuel only here. The fuel may be diluted with some diluent, like nitrogen or some other diluent. Okay. Or you can have air diluted with some diluent also. Okay. So, that is to change some certain properties of the flame. People have used this configuration also. Okay, so, this is a slot burner. So, instead of a cylindrical jet, now you have this 2-dimensional jet coming out from here. So, this is the fuel jet and air jet. Then of course, you put some screens to make the flow pretty uniform. So, it's coming out from here, the fuel jet and then the air jet, and then you get like a 2-dimensional flame. Okay. So, you make measurements in the in the symmetric plane. This is the computed image of the flame for this configuration. So, the image if the flame is shown by the OH, CH, okay. And on this side, I think is the heat release rate. Okay. So, there is some gravity effect. You can see the flame is also bending because of some gravity effect. Okay. So, that's the jet configuration, axisymmetric flow. Then this is the counterflow configuration. So, I'm showing you all three of them: spherical, okay, cylindrical, and then counterflow. So, this is from experiment with syngas. So, you have the fuel, which is syngas, is flowing from this bottom nozzle, and from the top nozzle you have the air, and then you get this syngas flame somewhere in the middle. the flame may be on the fuel side, but more typically the flame will be on the air side, that is away from the stagnation plane toward the air nozzle. So I'll show some more detailed results on this flame also. Same counterflow we can also do partially premixed flames by having some air mixed with the fuel in the fuel jet. So you add some air and then you control the amount of air. So when phi is 10 here, that means just very small amount of air, so that the equivalence ratio is 10. If there is no air, the equivalence ratio will be infinite, right? And then you add more air to the fuel jet, so then equivalence ratio is 5, 3.5, 2.5. Then the flame behavior changes a lot. You get two distinct reaction zones. The bottom one is the premix flame, and on the top you have the diffusion or the non-premix flame. So they get more separated when you have lower equivalence ratio. As you increase the equivalence ratio, these two flames come closer to each other, and it's here almost looks one flame. So for counterflow flame, this is the flame structure. So again, we look at where the flame is, and then we plot all the properties along this axis, along the center line, going up. So from the fuel side, Z value will be 0. So it's plotted from 2 to 8 millimeter. I don't remember the exact distance. I believe it was probably 10 millimeter. The distance between the two nozzles. So if you plot along this Z variable, again you see that the fuel, so this is, there is a nitrogen dilution here, so the fuel mass mole fraction is like 0.15. The rest is nitrogen on this side. And that was done to keep the temperature lower. And also to compare with the experimental data. The experiments were done with the high amount of nitrogen dilution. So almost 85% nitrogen, 0.15 fuel mole fraction, but the structure is very similar. You get the fuel mole fraction going to 0, so flame is located right here, which you can see from the temperature plot. So the temperature peak is around 6 millimeter. So that's where the flame is located, more like 5.7, 5.8 millimeter. Oxygen is coming and going almost to 0 at the flame, and then the CO2, H2O peak near the flame. And then you can see the temperature and the velocity distribution. And this increase in velocity is the expansion at the flame, which we talked for premixed flames also. As the temperature increases, density decreases, right? So correspondingly, the velocity increases to satisfy the mass conservation. And then for this flame, in this paper, we computed a lot of other species, including benzene, the aromatic species. This is for a different fuel. So hydrogen, air, non-premix count, but the flame structure is very similar. Temperature peaking. The stagnation plane is here where the velocity goes to 0, which is right here. So this is the fuel side. This is the oxidizer side. So you can see the flame is now located on the oxidizer side. Now the flame location corresponds to where the mixture is stoichiometric. So that's a very important property to remember when you analyze this, jet flame, the diffusion flames. So flame location is, okay, flame location corresponds to where fuel and oxidizer, oxygen, they meet in a stoichiometric proportion. Okay. So if you, so give you an example, let's say you start diluting the fuel jet with nitrogen. Okay. So which way will the flame move? Oxidizer side or the fuel side? Okay. Because you are reducing the amount of fuel, okay, in the fuel stream. Okay. So the stoichiometric condition will say, okay, you have to go toward the fuel side, okay, because you're reducing the mole fraction of fuel. Okay. Same thing happens if you in air, okay, you put more nitrogen. Okay. So if you add more nitrogen, now you are reducing the oxygen. Okay. So the flame will move toward the oxidizer side. Okay. If you have more oxygen, okay, like oxygenated flame, let's say the oxygen mole fraction is 0.5 in air. So then this flame is going to move away from the oxidizer side toward the stagnation plane, or maybe, okay, on the fuel side. Okay. So again, why the flame moves? Okay, it goes to the location where the stoichiometric condition is met. Okay. The rest of the properties are, behavior is very similar. Okay. So let me see the hydrogen. Yeah, this is H2, and from this side O2. O2 is here. Okay. So again, the flame is somewhere here, and then you can see the major product H2O peaking where the temperature is peaking. So whatever fuel you take, whatever condition, so the basic structure is very similar. Okay. In this diffusion flame. Okay, now after the introduction, we are going to cover, okay, some of these topics, mainly these. So we already did the introduction. First, we are going to spend few minutes understanding the mixing behavior of a laminar jet. So if you have fuel jet, okay, issuing into, okay, quiescent air, okay, how does the mixing take place? Okay, what is the fuel and oxygen mass fraction distribution? What is the velocity distribution in a non-reacting jet? Okay, and you'll see that those results, okay, will tell us a lot about the properties of the flame itself. Okay, so from the non-reacting jet, then we'll analyze the laminar jet flame. Okay. So what is the fuel distribution, oxidizer distribution in a laminar, and what is the temperature like in a jet flame? Okay. Now for a jet flame, flame length is one of the fundamental properties. Okay. How large is the flame? Okay. So we'll discuss, how to calculate this flame length. Okay. For different configurations, and also what is the effect of various parameters, on the flame length. Okay. And then I'll just show some results on counterflow flames and partially premixed flames. Okay, so these are some, okay, overall feature properties of the jet flames, not the jet flames, the laminar diffusion flames. Okay, so the fundamental characteristics which I emphasize again, in fuel and oxidizer are unmixed before they are transmitted to the flame. Okay. So the flame is separating the fuel and the oxidizer. Okay. So these flames are much more common in practical systems compared to premixed flames. So these are some of the examples. Fuel droplets, spray combustion and fuel droplets, both are related. Now, in some of these diesel and rocket engines, these are not like pure diffusion flames. They become partially premixed flames. But the diffusion combustion provides, significant part of the energy. Okay, like in a diesel engine, okay, maybe 20–30% comes from the premixed combustion. Okay, a lot of it comes from the non-premixed or the diffusion combustion. Also, when you have these partially premixed flames, the diffusion flame part has the highest temperature. Why? Because, again, fuel and oxidizer, they are meeting in stoichiometric proportion. Okay. So, since the diffusion flame has the highest temperature, most of the NOx is produced in the diffusion flame. Okay. So, there, the study of diffusion flame is very important for emission point of view also. Whereas the soot is produced more in the rich premix, flames when you have partially premixed flame. Okay. So, like in a diesel combustion, soot is produced in the premixed part of the combustion, and the NOx is produced in the non-premixed part of the combustion. Okay. And then other examples, candle flames, okay, typical diffusion flame, the cigarette lighter flame, the fuel there is butane, and that's a very typical diffusion flame. Pool fire is more complex, but a lot of burning is going on through the diffusion flame. Okay. Then there are other applications like solid combustion, solid fuel combustion, liquid fuel. They contain significant regions of non-premixed combustion. Okay. This should be combined, pool fire or fires. Okay. Most residential gas appliances. Okay. Now, I should not claim this is for everywhere in the world. This is more in the US. I don't know, like Europe or Asia or India. Okay. What kind of gas burners? Premix. Yeah. But the, like in US, the heating is all central heating. So there is one furnace somewhere, in the house, which is supplying hot air, the heating to the whole house. So that furnace, is non-premixed flame. The fuel is natural gas. Okay. So that premix burner, the furnace burner is non-premixed flame. So that's what I mean by residential burners. And of course, studying laminar jet flame is like a fundamental, combustion problem. And we study this because, for turbulent flames, it is important to understand the laminar flame also. So it's one of the classical combustion problems. Okay, so these are summary of the specific topics. So we'll start with the important characteristics. The emissions part, that will be tomorrow. I have a separate section on emissions. Okay, not just for diffusion flames. So these are the important characteristics we'll study when you in this overall diffusion flame topic. So we'll start with the scale analysis. Okay, here the reference is the Terns book. Okay, but Coe's book people follow, so you can find very similar equations in other books like Coe's book. There's a C.K. Law book, so you can find those similar equations. So we'll start with the constant density solution, and then look at some flame characteristics. We'll discuss this flame sheet approximation. This part, I'm not going to include the conserved scalar approach, okay, in these lectures. So this bullet and the next 3 bullets are not included, but then we'll discuss in detail the flame length, okay, and then various solutions for the flame length. Okay, so we'll start with the scale analysis. So for scale analysis, we just look at a typical jet flame. So let's say this is a flame. So as I said, you define one of the most important properties is the flame length. Okay. So here your velocity say VE. So here we can compare the flow time, or I should say the convection time, so convection time can define based on the length and this velocity, right? So LF divided by V. This is also like the residence time, you can say. Okay. And then you have the diffusion time. So diffusion here means, mass diffusion. So the convection is primarily in the flow direction, whereas diffusion is in the radial direction. Okay. So that determines the radial extent of the flame. Okay. So the diffusion time will be R square, because R is the jet radius here. So this is R. So that means the radial extent of the flame, is related to this jet radius. So so that's our characteristic length in the radial direction divided by mass diffusivity. Okay. Remember we did the similar thing for premix flames. So for every configuration of flame, what we need to do is recognize what is the characteristic length, what is the characteristic velocity, and what are the characteristic times. Okay. For premix flames, what was this quantity? This was SL divided by the flame thickness divided by SL. Okay. Or we used for the diffusion time SL square divided by the thermal diffusivity. Okay. So it's very similar. Just have to use the right length scale and velocity scale. So since there is a balance between the convection and diffusion, so we can equate these two characteristic times. So this gives us a very important result that the flame length is proportional to, I think I'll move this side because there is an echo this side. So flame length is proportional to V R square over D. Okay. And this is a very fundamental relation which can be proven experimentally. Okay. So without solving any differential equations, you are able to get a very important result. Okay. That the flame length increases with the jet velocity. Okay. It increases with the jet radius as R square, but it decreases with the diffusivity is higher. Okay. So a hydrogen flame, the flame length will be less compared to hydrocarbon flames. Okay. Also, you can recognize what is V times R square. Okay. That's the volume flow rate, because if I just multiply by pi, divide by pi, it becomes the volume flow rate of fuel because basically in the fuel jet, okay, let's go back here. Basically in the fuel jet, this will represent the volume flow rate of fuel. इसको
सर मैग्नेट की वजह से कर रहा हूँ.
Oh, अच्छा. Okay. So QF is okay VE pi r square. Okay. So the flame length for laminar flame diffusion flames, flame length is linearly proportional to the volume flow rate of fuel. Okay. And that's what you typically do, right? In a diffusion flame burner, you increase the flow rate, the flame length increases. Okay. And then inversely proportional to the diffusivity. Okay. Now this result LF being proportional to V R square over D, okay, has been shown to be valid for turbulent flames as well. Okay. But for turbulent flames, we have to recognize what is the length scale and the velocity scale. Okay. The velocity scale is the fluctuation, some RS value of turbulence velocity. Okay. And the length scale for turbulence, let's call it LT, is proportional to R, assuming that the phenomena is governed by the large eddies. So then the diffusivity, the main thing is here this is the laminar diffusivity. For turbulent flows, this diffusivity is much smaller compared to the turbulent diffusivity. So the turbulent diffusivity is proportional to U prime times LT. The characteristic turbulent length velocity scale and the length scale. Okay. So velocity scale is proportional to VE, the length scale is proportional to R. Okay. So this is proportional to then VE times R. Okay. So that means for turbulent flames, the flame length will be, this D now is replaced by V times R. Okay. So the flame length is proportional to then R. Okay. But the basic relationship holds for the turbulent flames, okay, except the diffusivity now is replaced by the turbulent diffusivity. Okay. And there is a classical well-known diagram showing this effect. Okay. So this I got from the internet, but a lot of books have this, this diagram. Okay. So the flame length here is called height. Okay. Plotted versus the velocity. Okay. So for the laminar regime, okay. So you can see that the length increases linearly with the velocity. Okay. Now then it starts becoming, as you increase the velocity, jet velocity, at some velocity flow will start becoming turbulent. Okay. So you remember what is the criteria for turbulent, transition to turbulence? Reynolds number, right? So jet Reynolds number. So somewhere maybe around 2000. Okay. So then there is of course transition. It's not that suddenly it becomes turbulent. So this part is laminar, then part of the jet is turbulent, and then the flame length first decreases a little bit because turbulent diffusivity is higher compared to the laminar. Okay. So it starts, and then when it becomes fully turbulent, there is always a small portion laminar, but so you consider this fully turbulent, then the flame height or flame length becomes independent of the jet velocity. So that's what this is. So, remember this equation now we got without solving any differential equation. When we do more refined analysis, we will see that this is still going to be valid. What is missing here is some kind of a constant, okay, and maybe some other properties. Okay. But these three properties will still show up: the jet velocity, jet radius, or the volume flow rate divided by the diffusivity. So, let us note down some of the assumptions involved in the constant density solution. So, we are considering now a steady laminar jet. Okay. Actually, maybe this is a misnomer, jet flame, let us say laminar jet. We will extract some flame characteristics without actually analyzing flame. Okay. So, a laminar jet, but let us say flame established by a gaseous fuel jet of radius r issuing into, so we will consider quiescent ambient. Okay. So, I think there is not either into quiescent ambient. Okay. Now, these are the major assumptions. So, start with say axial diffusion of momentum, species and energy negligible compared to radial. So, the radial diffusion dominates, okay, compared to the axial diffusion. Okay. So, this is like a jet mixing layer, which is like a shear layer, or so shear layer flow. Oops. So, this flame, these lengths, axial lengths, are much larger than the radial lengths. Okay. So, this may be of the order of meter or half meter, okay, or like 30-40 centimeter, where this will be, okay, about a centimeter or so. Okay. So, this is much larger. So, what does that mean? So, if you have dy f dx, okay, so x is much larger than x is much larger than r. So, this will be much smaller than dy f dr. Okay. So, this one dominates compared to this. Okay. So, when we write the equations, you have the axial diffusion and the radial diffusion. So, we will neglect the axial diffusion compared to the radial diffusion. Okay. So, that is the first bullet here. The axial diffusion. So, not only for species, for also momentum and thermal energy for temperature is negligible compared to the radial diffusion. Pressure is uniform in these flames. So, that is another good assumption. So, total momentum flow rate becomes constant. So, we neglect the viscous forces, we neglect the pressure forces, then the total momentum flow rate will become constant. Because we remember the rate of change of momentum is due to the pressure forces and the viscous forces. So, if you neglect those, the total momentum flow rate becomes constant. So, we will make use of this assumption in the analysis. Okay, this is again standard assumption, and the diffuse species diffusion, we use the Fick's law, and then we assume all the diffusivities are equal for all the species. Okay. Okay, this is also an assumption needed for solving the equations. Okay. So, Schmidt number is equal to 1. So, what is this new there? Okay. For the Schmidt number? Yeah, that is the kinematic viscosity. Okay. So, what does this do is you will see that the governing equation for the x momentum and the governing equation for y f, they will become identical, okay, for non-reacting jet, okay, when the Schmidt number is 1. Because in the momentum equation you will have nu, whereas in the species equation you will have d. So, if they are equal, then the equations will be identical. Okay. So, that means whatever is the solution for the momentum equation, we can use the same solution for the species equation for y f. So, using these assumptions for non-reacting constant density jet, there is an analytical solution. So, we will discuss that analytical solution. Okay. So, solution is given in several textbook, even fluid mechanics book, they have that solution. And basically, that solution will give us the Vx velocity, the axial velocity as a function of x and r. So, x is the axial coordinate or the radial. So, it will give us Vx, the radial velocity and y f. So, we do not consider the energy equation because it is a constant density jet. We do not consider the temperature distribution. And from this solution, we will get some flame properties. Okay. So, now I will discuss on the board some basic jet flow properties, and then we will write the equations maybe after the break, but let us discuss the qualitative properties. So, now we are considering a fuel jet. So, let me increase this size here. So, let us look at the distribution of YF, the mass fraction of fuel. So, we can consider inside the jet it is 1, right, and then there is a potential core. So, what happens is this fuel jet comes out and starts mixing with air. Then initially, this is the mixing layer where fuel and air are mixing. Okay. So, what does that mean? That if this is the potential core, so if you plot y f versus r here, what is the distribution? Let us say at x equal to 0. Okay. So, y f is 1, and with radial direction it is 1 up to r equal to capital R, and then it is 0, right. Okay. So, that is the variation of y f in the radial direction. But if you are say here somewhere, okay, at this x, what is the distribution? So, if you start from the center now, this location. So, from here to here, this is all fuel. Okay. On this side, it is all air. So, here you have both fuel and oxygen, or fuel and air. Okay. So, if you plot it here, then y f is 1, and then it decreases to 0 at this point. Okay. Now, we will come here where these two shear layers meet. Okay. So, at this location now, okay. So, at this point it is still y f is 1, but then it starts decreasing. Okay. So, at this location, if you plot y f is 1, and then it decreases. Okay. Actually, I think this is more like this kind of distribution. Okay. And now, if you go further downstream, okay, the y f will start decreasing at the center line also, at the axis of symmetry. Okay. So, y f is 1, now you start decreasing. So, if you plot somewhere here, so y f maybe say 0.8. less than 1. And then of course, it will go to 0 as this jet spreads in ambient. Okay. And you can imagine that there is some position where this YF will be equal to the stoichiometric value. For example, for methane flame, stoichiometric value of YF is about 0.055. Okay. So, you can imagine that will determine the flame length, where YF is close to 0.055, because flame surface corresponds to the stoichiometric mixture. Okay. So, if we can determine the YF distribution in a non-reacting jet, we can kind of see where the flame is there. We can determine the flame surface. Okay. Now, similar behavior applies to the axial velocity distribution, or if you consider a hot jet, temperature distribution follows a very similar behavior. Okay. So, what is shown here is this is the axial variation of YF. So, if you plot along the x axis, so now versus x, YF. So, up to certain length it will be constant, right. So, value is 1. So, this is 1, and then it starts decreasing. Okay. So, where the value is like 0.055 or YFS, that value of x gives us the flame length. Okay. So, that is, so it's showing little bit differently. YF is plotted on the x axis, I am plotting on the y axis. Okay. Maybe that way is better, because it's showing along the center line. Okay. But it's the same behavior. It is constant up to here, and then it decreases. Okay. And this is the distribution of YF with respect to radius. This is at x equal to 0. This is at this location where now it is already reduced below 1, and let us say this is close to the peak value here is close to YFS. Okay. So, now we will get the analytical solution, understanding this behavior first. Okay. So, our starting point is these governing equations which we discussed a couple of days back. Okay. So, here the mass conservation equation, then species equation, momentum equations. Okay. For non-reacting, we do not need the energy equation. Okay. And now we write these equations in the cylindrical coordinates in terms of x and r. Okay. So, now I will switch to the terms book to show those equations. Okay. So, now we consider steady flow. So, this is the mass continuity. Okay. So, d rho dt term becomes 0 for steady flow. Okay. And then you have the divergence of rho times v, right. Okay. So, for the r and x coordinates, that is the continuity equation. Then you have the momentum equation. Okay. So, this is the axial part. So, this is the equation for Vx. Okay. So, the rate of change of Vx due to the axial flow, this is due to the radial flow. Okay. And then this is the, where is this coming from? This is called the diffusion of momentum, or from the shear stresses, viscous stresses. So, mu is the viscosity, and you see the axial part here is neglected. What is the axial part? So, focus on this term. So, that is d dx of mu then dvx dx. So, this part is neglected compared to the radial diffusion. Okay. Now, we will not worry about this term, but this comes due to the buoyancy effect, okay, because the density rho is different from the ambient density. So, that gives it buoyancy force. Okay. So, that is the force term. Okay. Species equation is very similar to the momentum equation. If you neglect the buoyancy term, that becomes almost same. Okay. So, this is the axial convection or radial convection. Okay. You see, you can basically replace this Vx by yi, so you get the same term. Okay. Then this is the radial convection. Again, difference is Vx here, yf here. Okay. This is the radial diffusion of momentum. This is the radial mass diffusion. And if you neglect this, you can see this is replace this mu by nu times rho. So, here you have nu, and this equation you have d. If the Schmidt number is 1, okay, they become identical when you neglect the buoyancy force. Okay. Then the solution of this equation will be identical to the solution of this, provided the boundary conditions are also same. Okay. So, this is the starting point. So, you have equations, 3 equations basically, the continuity, okay, and then the axial momentum, okay, and okay. So, you can go through more details. We do not really need the radial momentum equation, okay, when we use the condition that the pressure is constant, and then the species equation. Now, if it is a non-reacting jet, we just need this equation, because the other species you can get from the fuel. Okay. For non-reacting jet, you only have 2 species, air and fuel. Okay. So, mass fraction of air will be then 1 minus yf. Okay. So, then you have a complete set of equations. If you have a reacting jet, of course, then you need equations for yf. So, in the book they have done, they use 3 species, fuel, okay, oxidizer, which is air, and the products. Okay. So, for non-reacting constant density jet, we just need this equation, and yf equation. Okay. Now, for constant density, we will make another assumption, the rho is constant. Okay. So, when the rho is constant, then of course, buoyancy term automatically drops out. Okay. So, then the equations are further simplified, and those are the equations we will consider in the first part of the analysis. So, those equations are given on page 333. Okay. So, these are the equations for the constant density case. Okay. So, if you want to study this in more detail, you start with the governing equations which we derived 2 days ago. Okay. Then write those equations for the cylindrical coordinates r and x. Okay. The species, momentum, and the mass continuity, those equations. And then make the assumption in the radial, the axial diffusion terms are negligible compared to the radial diffusion. And then the next step is you assume constant density. Okay. So, for the time being, we are not considering the energy equation. Okay. Just the continuity, species, and momentum. Momentum also axial momentum. So, 3 equations. So, with constant density assumption, Those are the three equations. Mass conservation, okay, because density drops out, and the axial momentum conservation, and the species conservation. Species means YF. Okay. Then the other species, the oxidizer, is just 1 minus YF. Okay. So let me see. Let's take a break here, and then we'll continue with these equations.